right, so that's the title of my talk, which I completely hate now. And I thought it was awesome when I picked it, but then I grew to hate it. So let's get into it. So I'll start with a short recap of 2D geometry. And first of all, let's see what a polygon is. And it's just across the broken line in a plane. In a plane. There's a word missing there. Can't believe I missed that. The number of vertices equals the number of sides. There are only straight lines as sides. There are no arcs. And there are no 3 successive points on the same line, because you have 3 successive points on the same line, 1 connected to 2, 2 connected to 3, 3 connected to 1. That's not a polygon. That's a damn line. So these are a few examples. Concave, convex, convex and regular, and then a circle, obviously not a polygon, and an open line, obviously not a polygon. A few more examples, and 3 sides, 4 sides, 5, 6, and it's going on columns from the first column to the last. First row regular, second row irregular, third row regular, fourth row irregular again. And this is where you see such shapes. Like here you have pentagons and hexagons, and there are 12 pentagons and 20 hexagons. And this shape is exactly the shape of this. Does anybody here have a background in electronics, knowing what that might be? No. All right. So that's a carbon molecule. There are 60 atoms of carbon, and the shape is exactly the same as the one of the ball. Well, not exactly the same, because the ball is obviously round because of the pressure inside, but oops. There are also 12 pentagons and 20 hexagons. And these are also polygons. And these are star polygons. And they are regular polygons. And only the points in red, only those are the vertices. And all the sides are equal. And the points where they intersect, those are not vertices. And these are star-shaped polygons, which are different from star polygons. And let's move on. Let's see a bit. And this is actually the last slide that I added to the presentation, because I thought I was going to talk about this a lot, and I didn't actually explain it anywhere. Well, I did explain it in an article that I wrote a while ago, but I should put a slide on it. So the circumcircle is the circle on which all the vertices of a polygon are situated. Of course, not all polygons can have all vertices on a circle, but we're going to talk only about those that do. And the central angle corresponding to one side, for example, corresponding to side AB, is going to be this angle, AOB. This is the central angle corresponding to this side. So I hope that clears what a central angle is. So start from the simplest one, a rectangle. Nothing exciting there, width, height. And you can make it a square if you give it the same width and height. You can make it a parallelogram if you skew it. And let's try a more particular kind of parallelogram. A rhombus. A rhombus, and you can see this one has different width and different height. And you can see the angles. Okay, so the rhombus has all 4 sides equal. So you think that you get a rhombus by skewing a square. Well, let's see that. This is a square, so let's see what happens if we skew it. Well, it's not a rhombus. And you can see it better if I increase the angle. It's not. So why isn't it? What's happening here? Well, let's see first how the skew transform works. So we start with a square, and we apply a skew transform on it. So you can see that the skew transform, as any other transform, also transforms the system of coordinates of the element. It's not the same as it was before. And for every point of the initial square, applying the skew x preserves the y-coordinate and changes the x-coordinate, just the x-coordinate. And you can see for every point xy, the new coordinate after a skew is going to be x plus a and y. And for skew y, it's going to be x and y plus a. All right, but what is a? Well, to understand that, we need to go a bit into trigonometry. So, does anybody remember this stuff? Well, what a sine and a cosine and a tangent are. So, the sine is the ratio between the side opposing the angle and the hypotenuse, the biggest side, the one opposing the 90-degree angle. And the cosine is the ratio between the adjacent side, the one near it, and the hypotenuse. And the tangent is the ratio between the opposite side and the adjacent side. And now let's go back to this one. So in this case, we consider this triangle, and this point has coordinates initially. Let's go back. This point, it has initially coordinates 0 and y. And after we skew it, it gets here, and it has coordinates a and y. So this piece here is a, the distance from this point to this point. This is a. But this is half the initial length of the side. And this is the skew angle, which is 30 degrees in our case. And this, the length of this, is y. So the tangent for this angle is going to be a over y. So we can get a as being y times the tangent of the skew angle. So since the side of the initial rectangle was 2y, and the cosine of this angle is y over the hypotenuse, which is just half of the initial side, which means that applying the skew x gives us a lateral side of 2 times y over cosine of 30 degrees in our case, skew angle in general. So we need to scale down along the y-axis, and we need to scale down by the cosine. This is the factor. And I usually don't compute this kind of stuff. I usually use SAS, but I just wrote it like this time. And you can do more polygons with CSS. And you can get a hexagon by rotating, by skewing the... You can see it better if I do this. And this is the original element, and I skew it by 30 degrees, and then I scale it to make it a rhombus. And you can see that I undo the transforms on the child element. I undo the scale, and undoing the scale means scaling by 1 over the initial scale factor. So this is 1/866, and rotate and skew it by the opposite angle, -30, because it was 30, and then rotate it to get it right into position, and then scaling it back, because its height would be still. Don't comment code like this. You can also get a triangle if you just shift the whole thing, and that's a translate by 50%. And you can move the triangle so that it's in the center of the original system of coordinates. And it goes like this. And this translate, it's applied, this one here, it's applied on the original element, on the parent element, not on the pseudo element. And this value is actually the in radius. And it's the in radius for this kind of triangle. And of course, use SAS to compute it. And we can do more shapes, like a pentagon. And how would we do a pentagon? I first had this idea about a year and something ago. And I thought, well, first use a rhombus. And then inside of it, use another rhombus. And then inside that rhombus, use a square. And cut off all the outer elements, and we're left with this. This is the pentagon. And it's actually a regular pentagon. And let's break it into pieces. We can break the pentagons into 3 pieces, 3 triangles. And the sum of the angles in a triangle is 180 degrees. So we have 3 triangles, so the sum of the angles of the pentagon is going to be the sum of the angles for all 3 triangles. That's going to be 3 times 180, that's 540. And that means that we have to divide that 540 to 5, because the pentagon has 5 vertices, and 1 angle results in 108. So this is going to give us the skew angle for the first rhombus. And we get the skew angle for the first rhombus by subtracting 90 degrees from the value of the angle for the pentagon. And these are the general formulas, and you can find them on the internet. You don't need to remember them. And so we first get the first rhombus, rotate it, and we rotate it by half the acute angle. And this is the acute angle, which is 90 minus the skew angle. And the rotate angle is this over 2. And we skew it by 18 degrees, which was the skew angle computed previously. And we scale it down by cosine of 18 degrees. And now we need to get the next rhombus. We start with a square. And actually, if we don't apply any transforms on it, it's going to be the same shape as of the parent. Don't comment CSS like that. And undoing the transforms from the parent results in a square. And now we make it a rhombus. But it doesn't really look like before. It has the same center as the first rhombus. And oops. I think I blew that. Well, this thing should actually have this corner. It should have it up here, intersecting this side, somewhere up here. So how do we bring it up? And by what distance do we need to bring it up? Well, we're going to need a pentagram for that. Not this one. This one looks artistic, but it's kind of hard to see angles and stuff. So, but this is actually the first thing I found when I searched for pentagram. This, you can see it a lot better. So inside in the middle, this is a regular pentagon. And all angles are 108 degrees. And this is 72 degrees, and this is 36 degrees. And now we need to compute the distance. And the distance by which we need to move the red rhombus up is this distance y. So this distance y is the difference between this vertex here and this point here, yellow one. Yeah, you can see it yellow. And the difference between this big distance and this small distance here. And this big distance here is L times sine of 36 degrees, because this angle is 36 degrees. All right, and this one, the small one here, is A sine of 36 degrees. A being the side of the pentagon. But we don't know the side of the pentagon. Well, we can compute it. This angle is half of 36 degrees. So we know that this is half the side of the pentagon, so it's A over 2. So this side, the hypotenuse in this triangle, it's going to be A over 2 over sine of 18. But the side of the initial rhombus we started with is A plus A over 2 over sine of 18. And we get A from this equation. And I never actually computed. I always use SAS for this. And this is how I got the value, the translate y. And I put translate between the reverting the transforms for the parent and the new transforms to transform it into a rhombus. And now all I need to add is the square. And the square has the center in the center of its parent. And of course, I undid the transforms from the parent. But this looks wrong because while it's a pentagon, but it's not a regular pentagon, and we have to move it up a bit. So let's see by how much we need to move it up. This is a pentagon, and this is its incircle. This is the side of the pentagon, and we call it A. Half of it is A over 2. And the inner radius is going to be A over 2 over tangent of 36. So that's 13.67 out of the initial side. So we need to translate it up. That's why it's with a minus. So this is the regular pentagon. Move on to 3D, because that's actually my topic. That was quite a long introduction. Damn long introduction. And let's do a cube. Or not. It's actually pretty simple, and I've already written a lot about it, and it's really simple. Let's build something a bit more complicated, like this. This is a 3D shape, a regular 3D shape, with 12 sides, 12 pentagons. And another regular polyhedra is this one. It has 20 sides, 20 triangles. But first, let's see a few more 3D shapes. prisms and antiprisms. So what are these? They both have all vertices contained in just two planes. Top plane, bottom plane, and you can see them. The two bases are all identical. The lateral sides are all parallel for the prisms. And one base is rotated by 100 over n, n being the number of sides, with respect to the other in the case of antiprisms. All right, so let's see how we get a prism. We're not going to get the full prism. We're going to get just one lateral side of the prism because all the others are just the same. And we're going to get a triangular prism, which is why we start with a triangular base, and a square lateral face. The first thing is we translate the base. We translate it down by half of it. And now we rotate it around the x-axis by 90 degrees. And we rotate it by minus 90 degrees because we want the front of it, we want it facing down, because down is going to be outside the shape. But this is not right. The center is not right. We need to translate it back by the in circle. And we're done with the base. Now this is the lateral face, and we rotate it by half the central angle for the triangle. And for the triangle, the central angle is 360 over 3, which is 120. So half of that is going to be 60 degrees. And now we translate it along the z-axis. And it gets into position. And the other two, we get them just the same. We just add the rotated angle. We add another central angle. So it's going to be 60 plus 120, 180. And adding one more, that's going to be minus 60. So this is how you get a prism. Let's moving further. We can transform a prism into a cylinder if we keep increasing the number of sides and decreasing their width. And you can see how it goes here back and forth. And I could have got it more precise if I had used more elements, but didn't really want to animate too many elements. And we can change this a bit and turn it into an infinite strip. But first, let's see the code. And this is SAS, because there is no way in hell I'm writing 23 elements with the transforms. So this is the number of sides, and it's the number of sides. Ri is the radius of the in circle of the polygon. The Ca is the central angle. And we compute the width of a strip. And in the same manner as we did here, except it's the opposite computation. It's going to be the in radius. And the transform is basically the same, except we take into account the index when for the angle. And now let's see the infinite strip. We get this, oops, this isn't working. Oh, it started working. The infinite strip is starting from a cylinder, and we also apply a rotate around the x-axis. The rest of the code is just the same. There's just this one more rotate around the x-axis. And this, of course, looks a lot better if I use a lot more elements, like this. And there's a link to the live demo, which I'm not going to click because there are 100 elements here, and I'm animating it to make it look more realistic. And I have no idea how that is going to look on a projector. And this is also done in the same way, and there is a live demo, a real demo of it. And it's also using like really, really narrow line, 2 pixels. And I apply a rotate X, and what this rotate is going to do is going to rotate this ribbon, is going to rotate it like this. And the translate is going to translate it along the y-axis, which changes direction because of the previous rotate. And it goes from pointing downwards, goes to pointing like that, in that direction. And there is going to be another rotate y, which is going to rotate each line. And the translate, which is going to position it, it would be on a circle if we were to ignore the first two transforms. But there are also the first two transforms, which make it a bit of a spiral. And there's also something like this. And I've had a toy like this when I was a child, and I used to play with it. And somebody challenged me one day, like, do this with CSS. So I thought, all right, I'll do it. And it's done in approximately the same way as the ribbon, except the segments are wider. And I call this a worm, because we don't really have to limit ourselves to lines and strips and squares and stuff like that, and we can do this stuff with circles. And my dad was revolted. It's so pretty. Why do you call it such an ugly name? And the entire surface is rotated. So the initial y-axis points like this. And the translate simply moves each circle a bit more down, 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 down. And the rotate rotates it like this. And the translate positions it on, it will be a circle, if we were to ignore this translate, the first translate. And the rotate x makes it perpendicular. And the scale makes it go from this size to smaller, 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 until you can barely see it there. And this is the last surface. And this is simply an arc, because we don't have to take the entire circle, we can take just an arc. And taking the arc, we just scale it, because it goes from this long to just this long here. And then we just rotate it around itself, and we get this shape. So now let's move on. If the first shape seemed a bit complicated, we can just make it into pieces. And we can split it into two halves. And each half is like a cup with a pentagon as a base, and 5 more pentagons on each side. So let's see how we get this. We start with the base and the lateral face. And the base, we rotate it by 90 degrees. And then we translate it by the value of the incircle. And now we move on to the lateral. And we rotate it, and we translate it. And it's the same thing as for the prism. And adding up, if we add another angle, we get 108 and 180, and so on, the others. And it's all the same for the other sides, and the same for the other half. And now let's see how we make into pieces the other one. This didn't start right from the beginning. It's like this, and you split it into a pyramid and an antiprism. And maybe some of you are wondering why I showed you that ball at the beginning. Well, we can morph this shape into a ball. And this is actually not working right. And it was working right a few minutes ago. And I can't believe this. Damn it. Damn it. But I do have it working right. This is it. Yeah, this is working right. Leave it. Thanks.